I'll just introduce Roger for as long as it takes to get that going. Of course, one could go on. I was planning to tell you Roger Blandford needs no introduction, so take it away. But maybe I'll just say a few words about my personal experiences with Roger and his work. So I, of course, heard about the Electrodynamic mechanism. And I read the paper, and I was really floored. Coming from a relativist, we didn't know that, relativist background, we didn't know that much about it, but this was a paper that truly interdisciplinary plasma physics.
Can you hear me?
And relativity, and put it all together.
Hello, everybody. Okay.
Fundamental mechanism that is
and then I'm going to just flash my video real quick.
So he continued to do much more great work throughout a long career, and he's still active both research-wise and especially performing a lot of really important behind-the-scenes service for communities. So today he's going to tell us about black hole binaries.
Okay, well, thank you very much, Sam, and thank you and all of your colleagues for the invitation to return to Arizona, which I've visited many times over the years. And it's good to be back here amongst many friends and colleagues. And I gave some topics that I could talk about, and the one that was chosen was black hole binaries. And so I was scudding around trying to do things, and this is going to be one of these frustrating and infuriating talks that is a parsec deep and a gigaparsec wide. So it's going to be a lot of different, apparently disparate subjects, but they are actually they're actually connected in the slides. Whether they're connected in the universe is another question, but I leave you to make up your mind about that. Okay, so I have many collaborators here, the ones I'm currently working on the top line, but also historically many of these ideas come from the second group of collaborators, to all of whom I'm grateful and none of whom should be blamed for what followed. Okay, so I'm going to just give a very brief introduction to black holes. As I say, this is going to be very cursory. As you know, AGN were discovered spectroscopically in 1908 by Pfaff at Lick, and then M87 1918 by Herbie Curtis and so on. Then quasars came in 3C273, a combination of radio and optical observations, both of which were remarkable, and that was quasars. And then Sagittarius star, of course, was a story since the 70s, and stars being seen orbiting around it, which is a good idea, very much a good idea what the mass is. Binary X-ray sources were in practice discovered in 1960s, but recognized, particularly the black hole versions, through Cygnus X1, etc. And of course, we now know many X-ray binaries. Thank you very much. That's much better. Thank you. And I'm going to, in this talk, I'm going to talk about a particular one, which was very famous and has now sort of faded a little bit, but I'm going to try and tell you about it. I think it's really very important for reasons we'll come to. That's SS433, and it's one of the things observationally that's changed here. This is a binary, I'll say a little bit here about this, but I'll return to it. It's a binary X-ray source that where there appears to be precession seen spectroscopically and in direct imaging, as you see here, and it's inside an enormous nebula, W50, which is about 30 times the energy of a typical supernova remnant, and towards the center of the galaxy. It's enormous, and this has now become one of the prime TeV, several hundred TeV gamma ray sources. So it's a high energy object in its own right, independent of all the spectroscopy that's happening at the center in this binary X-ray source. We'll say more about that later. And so I think it's going to, independent of what I say, it's going to be important. Another manifestation of gamma ray bursts, black holes is gamma ray bursts. There were documented to be 300 different ideas in published papers. And I would think it's fair to say that 3 of those have survived as 3 very different physical phenomena, and 2 of them represent, if you like, the birth cries of a black hole. And then, of course, as far as black holes are concerned, there is the discovery of black hole mergers by LIGO in 2015, and one of the features of that, to which I will return towards the end of this talk, is the surprising and I think largely unpredicted and unexpected realization that many of these are enormous masses. Instead of being 10 solar masses, the sort of nominal size of a black hole mass, their combined mass that's formed is 250 or so solar masses and counting. So they're clearly high mass events there, and their provenance is not agreed or understood. And then finally, the other thing that's happened, which has been associated with black holes, in this case massive black holes, is the report of a nanohertz background by many radio telescopes doing pulsar timing. And here's so-called Hellingsdown correlation. There's obviously, this is very much a work in progress. Again, I'll return to this in combination with that at the end of this talk. So that's the sort of brief panoply of black holes. They're large and small, they're common, and they exhibit many, many different behaviors. It's not one thing. Okay, let's talk about them a little bit more theoretically or astrophysically. Of course, the great advance was in 1963, the same year that quasars were discovered, of the metric by Roy Kerr, which bears his name. And there's the event, and of course, it has an event horizon. You know all about that. There's an ergosphere around that. And within that ergosphere, an observer on a time-like geodesic must rotate in a prograde sense. And we'll come back to that a little bit later. Now, a point that I really want to make here is that there are two ways of using these black holes to power these impressive high-energy astrophysical cosmic phenomena. One is through gravity, where you might have a supply of gas. In this case, it's in a binary system, but it could easily be in a galactic nucleus. It forms an accretion disk. The gas spirals inward under magnetic friction, and then falls into the black hole, and that is releases gravitational binding energy, just like a satellite in the atmosphere. The other way of doing it is to tap the spin energy of the black hole. A black hole like this, if it's spinning as fast as it can, then it will have nearly 30% of its energy in a rotational form, and realistically, somewhere between a third and a half of that is extractable using magnetic field lines confined by surrounding gas and threading the black hole event horizon. And that can take out energy very efficiently from the spin of a black hole in an analogous fashion to what happens with pulsars. So black holes can be gravity powered and spin powered, and there are two forms. And this is one of the themes I will return to in this talk. So I'm going to say a little bit about that here because it may be a bit unfamiliar. And I think it's probably important just to go through some of this. We'll know about this, certainly Sam does. And basically, if you just look at magnetic field lines threading the horizon of a black hole and assume that things are stationary and axisymmetric, which is a good way to start, and then you can think about three frames orbiting the black hole. One of them is a frame that's not rotating with respect to distant stars, say, and that's the one in which one imposes conservation laws. There's also what's called a Zamo frame, which is a zero angular momentum frame. This is sort of a compromise frame that rotates in a prograde way, and this is the one in which you think about the dragging of inertial frames, and this is important to make this distinction inside the ergosphere. And the third frame that's important for these purposes is what I call a magnetic frame or an M frame. And that is one in which, if one thinks about what the emission is doing, then it will, it's the frame in which it's normal to think about the astrophysics of high energy processes and so on. And this will also rotate in the ergosphere, and they're moving with three different angular velocities. You normally describe this electrodynamics in terms of force-free formalism, where it's just Maxwell's equations, which you've seen on a t-shirt, and then the electromagnetic force density vanishes, And this works just fine. This gives you perfectly good evolutionary equations for the electromagnetic field, which you express in lots of different ways. And you can use this in this cartoon here. You can imagine magnetic flux surfaces here, just axisymmetric flux surfaces. There are also isorotational surfaces. They all rotate with the same angular velocity, and they're equipotentials and so on. So there's the voltage associated with them and an angular velocity, and there's a current that flows out it. So you've got a giant electrical circuit here, and that current goes way out into what will become a jet, and they carry away angular momentum and energy from the black hole. And these are just some sort of formal relations here. And what, for the moment, all I really need to say is that if in a source like M87, which we will turn to in a moment, and of course everyone here knows much about this, then typically you're looking about 10 exavolts of potential difference across the surface of the black hole. It's a battery with 10 to the 19 volts there, 10 to the 19. Think about that in the context of the LHC, for example, and in 100 petaamps in terms of current. And if you recall that it only takes a megavolt to make an electron-positron pair, then clearly sparks are going to fly in this environment. Again, I'll return to that in a little bit. Okay, all right. So basically what you do here is you extract the rotational energy just like you would do from a neutron star as an essentially invisible Poynting flux. It's an electromagnetic Poynting flux, essentially invisible. There is dissipation, and it happens in two places. One is behind the curtain. It's all very respectable, very bourgeois, and behind the curtain is where all the dissipation is, and you don't see it. And then the other part is remotely in a jet. So it's like a simple circuit with an internal resistance and a load. And so this is the particle acceleration, which gives you what the radio astronomers are looking at. So I said I'll get onto M87. Here's M87, and I really can go very fast at this here because you've heard plenty. And so here's brightness temperature. Here's the various attempts at mapping this. Here's it seen on many, many scales. And variability is important. Obviously, also, so if we say the future, and this one hopes, and I'm hoping as much as anybody else here that we'll get orbiting VLBI. Let's hope it happens. Of course, also Sagittarius star has been a prime target. It's different in many ways, both observationally and interpretively. These are brightness temperatures, of course, here. I want to make now some important astrophysical points, and these are ones that make me. I have heterodox views. I had from the first day I saw the paper on from the Event Horizon Telescope, and they're really rather different from what is said. So this will carry a government health warning. What I'm about to say. All right. So the thing I would say is in the roundest of numbers, the radio astronomers know how much power is extracted from the spin of the black hole. This is power, luminosity. And it's about 100 times what you can see from the gas orbiting the black hole. Okay, so most of the power is going off in that jet. That is what appears to be going on. Second point is the jet is continuously collimated. This is an observational point. I'm into the business of inferring from observations rather than doing lots and lots of simulations and trying to shoehorn the observations into them. Both are reasonable approaches. They meet in the middle, but this is what I would say. And so the jet is being collimated out to at least 10,000 gravitational radii, and so something is squeezing it in. The jet, you can map this in this and many other sources. The next thing is, if you ask what a reasonable mass supply is, in M87, it's not well measured, of course, but X-ray astronomers have tried, infrared astronomers will do with Webb, and the mass supply rate is orders of magnitude greater than the mass supply rate than the mass that appears to be flowing into the black hole. So 10 to the 25 grams a second versus, say, 10 to the 21 grams a second. It's like that. Even larger disparity in these numbers with Sagittarius star. To me, this is a big deal. To others, less so. And another point I'd make is M87 is famously an elliptical galaxy. In fact, most of the big radio sources, almost all of them, are associated with ellipticals, not spirals. That's an observation. It's been there since the 60s, and it's remarkable. Now, obviously, I'm going to say something that's heterogeneous, but I don't want to lose sight of the fact of at least having the opportunity to make a public tribute to those who actually made all this work. A large crew of radio astronomers, you know about it. They made the telescopes work together. They made the agencies work together. And the hardest challenge of all, they made the radio astronomers work together, and they produced a magnificent accomplishment. And that this we should never lose sight of, despite the fact that my interpretation might be a little bit different. Okay, so let me say in what sense a source like M87, by extension of many, many others, is different. Here are two competing cartoons of, on the one side, something that really exists only notionally, if you like. It hasn't really advanced a lot beyond the cartoon level. On the right-hand side are acres of prose in the scientific journal describing truly impressive simulations. I used to be involved with these simulations, but no way can I be anything useful in them. So all I can do is just admire what's done. But when all said and done, there are two very different views of what is happening. And this is what I want to try and explain here. The first, and the conventional view, is that, and this is an old cartoon from papers that I and others wrote in the 80s. It's an old idea that basically you get surrounding the black hole a very thick accretion torus supported by the pressure of hot ions accompanied by cold electrons. This was something that was recognized in the 70s, actually, and we wrote papers in the 80s about this. And so basically you make this sort of funnel, and that is what defines the jet. Now, there are more elaborate versions of this, but it's basically, most of these stories, it's something like that. And then most of the gas comes in more or less conservatively. What the arithmetic is, I still don't quite understand, but there's gas that comes in. It has a current sheet in the equatorial plane, the gas swirling around the black hole. It's going in very fast, and there's lots of emission there, lots of dissipation, and the field lines go into the horizon as sketched here in green. The alternative view, and so in this case, let me just say that the emission that you see from the Great Orange Ring and so on is coming from gravity power. It's gravity power that's producing this. Okay? I think now everyone accepts that the jet, it's rotation power. But the gravity power is what's making the emission. That's more or less implicit in most of these models. So I'm not going to go through them in detail and say that. So then the alternative view is that the whole business is rotation power. It's spin power. It's spin the black hole that's providing the power. And so not only is there this extraction of spin energy here, and just in case you're worried, there's enough spin energy in M87 to keep M87 going for another 1 trillion years. So we're not going to run out of power in M87. So here, this is rotation powered, and maybe 10%, no more, needed of what going into the jet is asserted to be going into the this disk, the gas out there. So you're applying a torque at the inner edge of this disk, sending energy out through the disk, and that is called not an accretion disk, but an ejection disk, another Latin construct, and all of the gas essentially that's supplied is expelled before it gets anywhere near the horizon. Okay, so that's the story. There is a region here. This is an, I won't, let me just leave it at that point. So what I'm saying is that the story that I'm saying here, that is that M87 is powered by spin, not gravity. What is seen, the supplied mass at very large radius is all essentially driven away from an ejection disk as an extensive MHD wind. And this goes out over many decades of radius, and this wind contains magnetic field, which is wrapped around the jet, just like in the solar wind, and that is what provides the collimation of the jet out to 10,000 gravitational radii and beyond. So the jet is collimated by an outflowing MHD wind. And that wind itself is collimated at large radius, a sort of outer boundary condition, by gas in falling at all latitudes from the cluster. A very different story from spiral galaxies, where the gas comes in the equator. In the elliptical galaxies, the gas falls in at all latitudes. And so that's the outer boundary condition. And the assertion is that that is what is necessary to make these impressive jets. If you didn't have it, then you wouldn't get the impressive jets. So here's another set of cartoons, and this shows my colleague Novi Gomez and myself our view of what's going on, seen on 4 different scales. Here's the ejection disk, here's the infall, as I said. Here's the radiation you'll see, and most of the gas will leave this disk at substantial radii away from the black hole. And so here's the jet. In M87, we're pretty confident the observers at a small angle to the jet axis, not that small, but small enough. And then if we look on smaller scales, then we have essentially a system where we're conserving mass, we're conserving angular momentum, we're conserving energy. There's a torque there, and there's obviously a giant circuit there. And this giant circuit has a potential, has a flux and a current that's associated with it. So think about this as an electrical circuit, if you like, and then you've got a wind here like that. So this is the outline of the model. As we get closer in, I'll call out 3 features. One is that there has to be some connection between the spin of the black hole and the inner edge of this disk that's hypothesized to exist there. And there are 2 mechanisms that are invoked. One is to say you've got field lines going through the disk like this, and there are instabilities, somewhat similar to the ones that are found in a regular accretion disk, so-called magnetorotational instabilities. They work here too, and they take angular momentum out. The other possibility, we call this the clutch for obvious reasons. The other possibility is the capstan, and this capstan are field lines that are almost certainly known as special little loops of field that are attached to the inner edge of the disk, and then those loops get into the horizon, and they too are very good at extracting spin energy from the hole. So these are 2 distinct but cooperative ways of getting spin energy from the hole, maybe 10% of what's going into the jet, out into the disk. The third feature of this, the third word here, where is it? It's what we call the governor, and this is an interesting process. For those who know some relativity, it's a thing called the Penrose process, and that basically says there are negative energy orbits for particles in the Kerr metric on time like geodesics, and you throw negative energy into a black hole, you take energy out. You're taking energy out. I'm angular momentum, of course. And the same thing can happen here electromagnetically. What happens is, if you imagine field lines going through the disk, going close to the black hole through the ergosphere, they will slow down until they reach the minimum angular velocity they can rotate with. At that point, what happens to the equations of force-free electrodynamics is they become non-evolutionary. The solutions, if you like, are turbulent. They make an electromagnetic disordered state, and all of that energy is essentially on a negative energy orbit going into the hole. So you're extracting energy not just from the field lines that are crossing the horizon, but the ones that are actually going through the ergosphere outside the horizon. You get more power out through this mechanism. So that's what we're claiming here. Okay, so that's a sort of, obviously we've done a lot more than this, but that's essentially what we're talking about. Okay, and then just to emphasize something I said before, these jets, as we have them considered here, it's not just a question of making some pea shooter on the scale of the black hole. It really is essential to consider 1 million gravitational radii in the whole description of what's going on. And it's like a tornado where you've got the bit in the middle that lifts the roof off a house. It's tiny compared with the large-scale gas flow that's going on. Okay, so it's a range of scales here, and that means something. So I've brought out a lot of ideas, and I'm going to continue to play with them. So the first one is that black holes are common, and they exhibit many different behaviors. The second one is that black hole power comes in 2 forms, gravity and spin. The third is that you extract the rotational energy for the jet and so on as an invisible Poynting flux, and the dissipation happens within the horizon. We don't see it, or at large distances where it'll make the emission that astronomers see. And then the final one is that M87 is powered by spin, not gravity, and the supplied mass, almost all of it in this interpretation, leaves the disk. And the wind collimates is collimated by the inflow at large radius, and then the wind collimates the jet. So it is transmitting, if you like, the effect of large infall to the jet. Okay, and then there's a large range of scales here. The problem to be understood requires exploring this large range of scales. So that's the summary. Okay, so this is sort of preamble, if you like. I was told to talk about binary black holes. Let's get on to that. And I can't really do full justice to this, but let me just start with this prefatory talk about binary black holes. Again, my sort of history on this is that I guess in 1980, Mitch Spiegelman and Martin Rees and I wrote a paper saying there should be binary black holes in galactic nuclei because galaxies formed through mergers and so on. And if every black hole has got a nucleus, every galaxy's got a black hole in its nucleus, then you ought to those nuclei ought to spiral. Those black holes ought to spiral in, and they ought to merge in the center through gravitational radiation and so on. And there was a bit of a problem because finding the Newtonian dynamical mechanisms for getting them to spiral in was hard, and it was possible that they wouldn't spiral in. What happened next is not entirely clear, but we thought that nature was cleverer than we were, and it would be able to solve this problem, and our expectation was they would follow in, and we expected that people would find lots and lots of binary black holes. Now, in practice, that has not happened. It is surprising how few that have even been claimed. And here's one of the most famous ones that has been claimed. It's called OJ287. It's a redshift of 0.3, and it has a quasi-periodic outburst like this, which Maury van Valtonen, my former office mate and so on, had claimed a 12-year period, which in the frame of the source becomes 9 years. And they predicted in 2022, I think it was, that there would be a burst. And I was part of some paper with it. Didn't happen. The outburst didn't happen. And so an extra epicycle had to be added. And so it doesn't mean it's wrong, but it's it's just observational evidence, and you can make up your own mind. But there's clearly something dynamically happening there. Quite what is not clear. So now. The thing that I've been, and a very good student, Andrew Sullivan, have been doing of late is sort of helping out my a long-term observational radio astronomy colleague, Tony Reedhead, and his crew of people who have been looking at and combining radio flux monitoring over 45 years or more in a variety of sources. Most of these sources are blazars. And blazars are sources in AGN with relativistic jets. And if I take Sam as an observer, he's very vain, so we'll take him as an observer. And so if the jet is pointed almost at Sam, then he will see it because of special relativistic beaming and so on. He will see it as very, very bright. So any flux-limited survey will contain overabundance of the ones that are beamed towards you. It's not paranoia, it's the ones that are beamed towards you are very, very bright. And these are called blazars. They were originally lac objects, and I was at the conference in 1978 in Pittsburgh, where they were first really discussed. And I made, with Martin Rees, gave a talk where I said, the blazars are ones that are pointed towards you, which was a rather controversial view at the time. And I can remember clearly Jeff Burbidge saying, in his way, this was, what were the ones that weren't beamed towards us like? And I said M87. So, and so one that's not beamed towards us is M87. So right now, what has come from this flux monitoring? Again, it's not clean, but it's pretty convincing. This is the best case of all. It's Parkes 2131, which has got about 7 periods of oscillation that are in phase. They're not continuous through here. What's going on here is a very interesting story. I haven't got time to explain it to you here, but this is Parkes 2131, it's got a 4.8-year period observed, 2.1 in the frame of the source, and this periodicity was both retrodictive and predictive. It is as though we take some data and fit a spectrum to it with relatively small, with that essentially that amount of data and the conjecture that it was a black hole. It predicted going forward, and then Sandra O'Neill and others found the old data which showed the same periodicity in the past. So I'm pretty convinced by this one. You see it not just at radio frequencies, you see it all the way up into the optical. And I'm normally more conservative than my observational colleagues, but in this case, I actually think it's there in the gamma rays, but they were not prepared to sign off on that. So you see, and there's a phase lag going up to about a half in the phase of the oscillation as you go up in frequency all the way up to the opticals. This, I think, is much the best case, and is now seen, and it was seen in the Active Cosmology telescope, and I have great optimism that the Simons Observatory will see many more of these examples of this, which we now have some good hypotheses to search for in that data set. Parkes 0805 is another blazer. Fewer periods, of course. You can say this is all red noise if you want, but I think we're fairly convinced that there's something there. But we'll see what happens over the next few years, see if it's predicted. And then a much more recent one is Parkes 1309. There are other ones which are less good than this, where you're seeing data like this. Again, only a few periods. You wouldn't believe it if you didn't know the other things. And again, the opportunity to be predictive. So without examining this data in any more, there's actually more sort of second order signals in the data here. I'm not going to discuss this to go through those. It will be sort of too complicated. The primary evidence is what I've shown you here for these three examples, no more. Okay, one of the things that I was particularly eager to do was to go after the optically spectroscopically and do optical spectra. I have to say it's, the typical conservatism of, I don't say people, we're not going to give you any time because there's, you haven't got a model. And so it just seems this is the sort of thing that cries out for taking spectra. And there are some historically, and you can see them here. And I won't claim there's a periodicity in the optical spectra, but that's the sort of thing you're looking for with a very open mind as to what you see what the spectroscopic response. So just in case anybody here ever has any access to an optical or infrared telescope, I can't imagine they would. If anybody wants to just take 5 minutes or whatever, these are bright 18th or 19th magnitude objects. They're not very hard. To get more spectra would be lovely, but so you would have some credibility in doing this that someone like me would never have. Okay, all right. Okay, so what's going on here? I'm going to give some sort of physical models here. So we examined quite a lot of several physical models, as have other people, as to explaining this data, including just straight red noise. But I think we're looking for physical models. Here's the one that one of the ones that we looked at quite seriously, made sort of models of, and that is to imagine we've got a jet, a blazar jet that's pointed at Sam like this, and then I'm going to orbit around a companion black hole in a mutual orbit, and then there'll be a transverse velocity associated with my orbital motion, and that feeds into the relativistic aberration, which gives you the modulation. Okay, so that's the fundamental model. Now, of course, you actually look along the line of sight through an optically thick transitioning to optically thin jet with radio emission, etc., etc. And we have models that do this. They're phenomenological because I have no basis for saying what the emissivity is the function of radius, but they are not inconsistent with normal radio astronomical presumptions and the usages. And so what you actually see at a given time is some small or sinusoidal oscillation in this jet, and you're looking at essentially a radio photosphere, and at a given time, this might be somewhere here, and then you can compute what the flux would look like, and then you can fit to the observations as done. And so we've gone through those sort of exercises. Obviously, the high frequencies go from ACT and so on will come close to the black hole horizon. The low frequencies will come from further out, And you can make models along these lines. There are more predictions in particular. It will be rather ambitious, but if you can get the centroids of these sources, they will show marginally measurable small displacements. It'll be hard. That'll be a real observational challenge, but it's not outrageous that you can see displacements. This is the sort of theoretical version. And as I say, just to go back to the emission line regions, here's the jet. In fact, old papers I did with Robert Emmering and ago was models for the emission line regions that are basically MHD outflows with gas associated with them. And what you're looking at is these clouds that are ejected by a disk like this with gas in them like that. And so you'll get outflows. And this is the sort of feature one is looking for in the emission line region of these sources if you do some optical spectroscopy. There are other possibilities, absolutely, for sure, but this is the sort of thing you're looking for. So it's not as though we're testing one well-trodden theory, we're just looking to see what you see. Okay, so that's that, and there are many observable consequences, and more, as I say, more sources may come from Simon. So this is basically the story that we're telling. So we've got this black hole here. We've got a disk called D here. We've got the wind here. And what we have done in the recent slew of models is a slight elaboration on what we did before, whereas before we were sort of sending the jet out with the speed, essentially the speed in inertial space of the source. In this case, what we're saying, and this is like what you heard about M87, is that what is actually moving around is the wind. The W here that's emanating from the disk, there's a wind going out from the disk, and it's the wind that is moving around, and then up the middle is a jet that is being told what to do by the wind. So this jet is moving in a sort of sinuous way in a channel defined by the moving wind. That's something, and there are restrictions associated with this, but it works basically. And this is an important idea, I think, for what follows. And so remember, it's essentially, as in M87, these sources, the direction is determined by the wind, and there's a jet that goes up the middle ultra-relativistically. Okay, so did I want to do that? Okay, so now that's as much as I'm going to say, unless there are questions on the binaries and the massive black holes and where we are. I've given a whole lectures on this, but this is a sort of top line summary, if you like. This is the parsec deep. Okay, so now I'm going to go on to a galactic source. I said at the start, SS433, which people of a certain age remember from 1980 when it was a big deal. It was the Rosetta Stone, etc., etc. And it has amazing properties. And it's kind of receded from view, but now it's come back into prominence, partly because of the gamma ray observations, but also because of something I'm about to tell you. Okay, so this is the nebula W50 in the galactic center. Towards the galactic center, it's 5.5 kiloparsecs away. It's enormous. There's about 30 times as much energy there as there is associated with a standard supernova remnant. It's 2 degrees across. So here's some dimensions here. There's SS433 in the middle, and it has these ears, so-called ears here. These are protuberances that are pushed out by an outflow from the central black hole. Here's its location in the direction of the galactic center. There's a galactic disk there. The spectroscopic work has come from my colleague in Oxford, Catherine Blundell, who's done a heroic job over many, many years, assembling spectroscopy using a network of telescopes around the world. There's now about 10 of them, and many of them are in girls' schools around the world. And so I don't need to explain why that's not a bad thing to do. She's assembled, well, here she is, she's assembled a huge amount of spectroscopic data, and a lot of that has already been analyzed. But I'll explain to you what has actually been discovered in this. This is just saying this is what the energies are, and the lifetimes, it's about 100,000 years. This has been about 100,000 years. Okay, so the spectroscopy, this is an old version. Basically, what was found in the 1980s was that there were moving, so-called moving in the spectrum lines. There was a red line and a blue line, and they could cross over. And then there was additionally a stationary line here. But forget that for a moment. These moving lines would move backwards and forwards with a period that was 162 days. And that 162 day period, we now know is extraordinarily well fixed. There's constant phase. It's like clockwork. It isn't just a sort of casual thing. It isn't gas dynamics. It's like clockwork. And so these lines move, that line's moved. And then in addition, there's even more mass flowing outwards. These are typically H alpha observations. There's more mass moving outwards like this. These are, and this is a stationary line, and it does show variability, this stationary line, but it's much more subtle. And within the observations of this so-called stationary line, which contains most of the outflow, is a period of 27 hours. And I'll explain what that means in a moment, but we're talking about observations at the moment. So in the 1980s, it was inferred that what was going on, and this is just a kinematic description, was if that is the black hole, fair enough, and these are two jets, they were processing about an axis like that in space, and these so-called moving lines were formed by gas moving along the surface of that cone, processing every 162 days like that. Okay? Now, so it's a 20-degree cone. That varies in a way that also has a signal. There's huge numbers of signals in here, and that has signals in it, but this period is a fixed one. And you can not only see these moving lines spectroscopically, you can see we now call these bullets, and they're sent out, more or less launched. Instead of a continuous jet, there are essentially bollards or clouds that are expelled every about once, roughly about once a day, and they go outwards. And then you can see them using radio astronomy. You can measure the shape that they make on the sky, the radio images, and you see the corkscrew that you would expect from sending features out like that on a precession cone. So this is kinematically what's going on. And there were many explanations for this. And here's W50 here. And let me say out here in the nebula here and out here, we now know these are X-ray observations from Rosetta and so on. They came out over the summer. These show the features going outwards. Here are the years and so on. So the stuff clearly going out in these anti-parallel directions. And there are LASSO, which is a magnificent spiral and magnificent telescope in Western Sichuan, which I've actually visited, and it has found several hundred PeV emission here, and 700 TeV emission here, nearly PeV gamma ray emission. So this is a prodigious galactic gamma ray source, and perhaps the source of the so-called near the cosmic ray spectrum, but I won't go there at the moment. And in addition, IXP, which is the X-ray telescope, which is polarization, has seen 40% polarization. And those of you who recall synchrotron radiation theory, that means there's a very organized magnetic field there. And it's been characteristic of many of these sources in this general class of rotating objects with magnetized rotating objects. They show enormous polarizations. That's prima facie evidence that there's currents flowing out there. So this isn't just some little dissipation locally. There's giant circuits in the Crab Nebula and Vela and so on and so forth. There are giant circuits there that are powered by a tiny little source in the middle of the show. Okay, so that's that. In addition, in SS433, there's a blue star. We estimated mass is around about 30 solar masses. I'm not doing justice to the analysis here. Let's just say that. And there's about a 10 solar mass black hole is the conjecture. These are very elastic numbers in terms of derivations, but it's certainly allowed. And this blue star orbits a 10 solar mass black hole with a 13-day period. That again has been known since the 80s. And so there's an X-ray binary. But our claim is that in addition, the there is a okay. Here's the gamma rays there. Sorry, yes. And the power in this source is essentially the energy of W50 divided by the lifetime, and that is much greater than the Eddington limit. So this is way above the Eddington limit. Okay, and so it, it kept driven by mass. So this the gift is still giving. There you go. Okay, so to try and explain our inference as to what is actually going on from the observations is that it's really a three-body problem here. I said there was a 27-hour period that we're seeing. The claim is that that's a star, maybe a solar mass. It doesn't really matter what it is. It's on an inclined orbit going around the black hole, an inner orbit with a 27-hour period. And this is the third body, T. It's orbiting the black hole, H. It was actually proposed as one of the ideas by Fabian et al. In the 80s, and it was a good idea, but they were very worried about various aspects of this, which I think worry us much less. And so that one of the things we can say is the orbit of this star must be highly eccentric in order to make this work. And what you're seeing for the precession is essentially nodal precession, just like the Earth-Moon-Sun system, the 18-year period of the Earth in the Earth-Moon-Sun system. And it's the same thing that happens here. And so the explanation, if you like, I don't know, people watch Netflix or whatever, the three-body problem. I like to show this because it's very similitude, because radio astronomers have a habit of collapsing their radio telescopes. And so, sorry, I shouldn't have said that. Okay. And then last night at dinner we had that, which there's a different metaphor there. Okay. So what we have here is the 13 solar mass primary. There's a black hole, a third body going around here. Here's the observer in this direction, and this orbit which in the TH orbit is inclined at 20 degrees, and then you can do three-body calculations and see what you can explain quite a lot of the periodicities that are seen here. I haven't got time to go through all of this. It wants to be long-term stable for 10 to the 5th years in the three-body problem, as in that is not necessarily true, and but in the models that we would use, it is true. And the proposal here is that in this case, where the mass supply is much less than much greater than the Eddington rate, rather than M87, where it's much less than the Eddington rate. But don't be ashamed. In the past, M87 would have been the brightest star in the sky in its prime. But we're all like that. The claim is that this is also powered by spin. Okay? And what's happening is a prodigious supply of mass is coming from the primary star, settling into an accretion disk, going past the T orbit, trying to get into the black hole, and being blown away by similar mechanisms by the spin of the black hole. And it's all this, the lines that you are seeing, the stationary lines especially, that's the gas being blown away by the rotation of the black hole. It's not gravity, it's spin that's powering this. Analogy that you can use, if you think back to the 19th century, the sun was thought to last 10 million years, 9 million years, I think, according to Helmholtz. And then Darwin and others showed that it was more like billions of years. We now know it's going to last 10 billion years. And so to cover their embarrassment, astronomers and physicists had to invent nuclear power. It all worked out okay. So there's a different power source going on. That's a sort of analogy, not to be pushed too far. So what we've got is 0.26 jets. These are the bolids, basically, that are launched from the inner edge of the accretion disk surrounding the black hole. The wind at about 1% of the speed of light is the wind from the outer disk radius inside the T orbit. And then there's also a prodigious amount of gas learned from outside the outer binary. There's a lot of gas going off in the wind from there, and there's a lot of observations of that. And then the final kicker in this, as well as these three different distinct outflows, the final kicker is the claim that inside the inner 0.26C precessing jet, there is an ultra-relativistic jet beamed well away from us, quite invisible because it's beamed at 90, more or less 80 degrees to the line of sight, and that is what is causing the PeV gamma ray emission. So there's in addition there an ultra-relativistic jet, and that's powered by the black hole spin, and it's designed to explain the PeV emission. Okay, so that's the story on SS433. Sam, how much time do I have? I think I started.
We started late. So if I were you, I would talk for 10 to 15, and if possible, get some questions in there.
Okay, I was hoping you would say less. So
That would also be fun.
if you think this is dodgy, wait for the next part. Okay. So I will speak very, very fast and give lots of time for questions. Okay. All right. Good. Okay. So so basically, just to summarize here, the claim is that in SS433, there's a high mass supply rate, much greater than the sort of so-called Eddington rate, and this is also spin power. And it's a leap of faith to say that something similar could be true for the high mass supply cases in active galactic nuclei. And these include the brightest quasars and so on. So the bright quasars in active galactic nuclei, the claim is that they too are predominantly spin powered. This is a big leap. It's a big conjecture. It's the thing I like about doing this sort of thing is this is unlike much postmodern astrophysics and so on. This is refutable. I mean, I think there's things that one can say. You can actually test these conjectures in a rather straightforward way. So the claim is that this is spin powered. You might say, well, how does a black hole grow? Well, again, the idea, which sort of goes back to the 80s, is that the time when it grows is when you've got an intermediate major mass supply. Those of you who have young children or have fed young children might observe that if you don't give them any food, they don't grow, and if you give them try and feed them too fast, they also spit it all up and they don't grow either. So you have to feed them at a regular rate. That's not a metaphor. It's not an experiment to be performed, and it's not a metaphor that needs to be pushed too far. But the point is that for a range maybe 100 or 1,000 in mass supply rates, there's no problem in having most of that mass grow the black hole through the gas channel. I'll come back to that in a moment. Okay, all right. Now for the stuff that's really off the wall. Okay. And I got into this not for what is going to be the ultimate, what's in the abstract, but was actually through this nanohertz background that was reported, the sort of nanohertz waves that were seen by a variety of radio telescopes, and and the many the Americans and so on, and Greenbank and so on, and especially Meerkat in South Africa has done spectacularly well here. Collaboration with the Germans and so on, that's done spectacularly well. But the future almost certainly lies with the fast radio telescope in China. That's going to be the premier, the successor to our Arecibo, and it's going to be the premier source of data and so on. So again, you might think about that. So the story that we were telling then, and this was pre little red dots and so on, so we'll come on to that in a minute, was that what was going on here, and it's a conjecture, and as I say, it's highly refutable. The first stars, the so-called population 3 stars with low metallicity, they form in the nucleus of a protogalaxy. The claim is that they form as a star cluster, the first thing to happen in a newly formed galaxy in the nucleus, and these will evolve rapidly on timescales of millions of years to maybe nominally 10 solar mass black holes. And if the thing that you start off with is compact enough, and that's the challenge, but if it is compact enough to start off with, then it will enable core collapse of the sort that has been invoked in globular clusters and other star clusters and so on in dynamical processes in a more sedate way. This will, of course, be surrounded by neutron stars, more slowly evolving stars, and lots of other rubbish around associated with the first generation of stars. And the idea is that the periods that you would be typically seeing in these sources would be of order years. That is to say, for nanohertz band, it's periods of order a year or thereabouts. The size of this cluster would be, say, nominally, obviously, was doing integrals here in 10 to 50 centimeters, and the speed's maybe about 1% that of light, so the dynamical speed. So this is not a globular cluster. This is a much more compact thing, and it evolves relativistically. And the conjecture is that these star clusters have enough angular momentum to start rotating, and as they collapse, they develop bars. And those bars, like fluid ellipsoidal figures of equilibrium and so on, can radiate coherent gravitational radiation. Not just two objects spiraling around each other, they make coherent gravitational radiation. And most of the background, I had a problem with this observation. As soon as I saw it, it seemed to me it was too high. Now, people have claimed that you can just about accommodate it, provided black holes are assembled from binaries, and you can maybe just accommodate it in a way. And they found slightly more high mass black holes and so on, which certainly helps. But, you know, black holes up in galactic nuclei have a day job. They've got to make quasars and active galactic nuclei for the gratification of optical astronomers like Rob Kennicott and so on. And they have to do this as well. And I think there's too much energy in this background for the source that's claimed. So we know what the black hole density is locally, and we can't get any more than that. A clear prediction here is if the radiation that is being seen is not from binary black holes, but in fact is coherent radiation, is the spectrum, which is not yet well measured, will be different from the canonical spectrum, gamma 11/3 and so on, that is predicted for binary mergers. So that's a very clear prediction here, and we'll wait and see on that. And there's another reason for invoking this. And remember, I drew attention to the fact that LIGO had seen lots of high mass mergers, up to 250 or so solar masses so far. And this it points to a sort of hierarchical assembly of black holes. And so the conjecture is that within this cluster, the black holes would merge, sort of more or less in step. They would radiate coherent gravitational radiation, and this would be a site, perhaps, for in the more local universe, for some of the high mass systems that are seen by LIGO, because it's part of a sequence. You won't see the higher mass black holes because LIGO is not sensitive to them, but up to a few hundred solar masses, you can certainly see them, and the claim is they're seeing them. Now, there will be a highly intra-cluster magnetized medium there, almost certain. There will be gas there, and through processes that I've been thinking, again, this is all very much work in progress, but I'm thinking about, you can extract these black holes that are made are spinning very rapidly. I can extract the energy electromagnetically from them, not through accretion, but through electromagnetic processes, and put lots of energy into the surrounding gas. And as well as the supernova themselves, this gas will be blown out to make a photosphere. That was sort of what we were thinking about and talking about time. And so what you go is this cluster, maybe of a million black holes, become a triple, and then a binary, then an AGN. Okay, and then it can start accreting, as I say. And one of the features of this is you can grow this central black hole mass much faster than just by accreting gas at the Eddington rate or so on. In fact, you don't have to. You are limited by the Eddington rate. There are many mechanisms for accreting faster than that, but if you believe that's a limitation, then this is a way around it. Okay, so this is an alternative scenario to the increasingly popular massive seed scenario, which says there's a collapse of gas or whatever at early times to make a million solar mass black hole, and then it gets on its business of growing more and more. Now, what has happened since then is, again, no one here needs any introduction because it's very much a local industry, is the magnificent observations by James Webb Space Telescope of what have been called, for interesting reasons, which you again know, little red dots. And so the question is, has what I've just shown on the last slide got anything to do with this, or are these little red herrings instead? And so, as you know, the claims that there are maybe 100 million of these things on the sky, 30 times as many as regular quasars, redshifts out to about 10, slightly less than that. Most of them at high redshift, but a few of them being seen at low redshift, not quite clear. Lots of things being discovered here. Some of these statements may already be wrong because I haven't been reading the literature, but they have distinct infrared structure with so-called spectra at the Balmer break. So this is a sort of rather distinctive spectral feature. Again, there's some story to tell with that. X-ray and radio quiet, and very few stars surrounding them. That's what we're seeing. That's a little royal. You and all the heroes who made such a magnificent telescope out of James Webb. And you know, like to say, it's yeah. I don't know whether this was divine reward for the exemplary behavior of astronomers, or the other theory is that some remarkably talented people made this thing work, and the engineers all over the place, managers, astronomers, even all of it, and it's truly something to be proud of. It's even better than they say it's in the newspapers. It's fantastic. And so one of the many discoveries it's made is this, an interpretation, again, a little fragile, the 100 parsec photospheres, variability from a cluster, 100-year variability maybe, and low density of elements with heavy elements and dust and so on. Again, these are somewhat fragile inferences on the basis of observations. People here know much more than I do, and are eager to be told which of these are wrong. You know, I sort of, when I first heard about this thing, I say, well, was the Milky Way ever a little red dot? And most people who worked on standard theories of galaxy formation said, no, this is a sideshow. And then almost everybody else said, oh, it must have been. And so it'll be interesting to see whether which of those turns out to be accepted. But I would say it's telling us that galaxies form from the inside out. I used to give talks about, you know, about 20 or 30 years ago, about, you know, how black holes could grow and all of that. And I used to say, you know, which came first, the galactic chicken or the black hole egg. And my thesis was that they were co-evolving. They were like developmental biology. They grew together. But now, if this is any sense to it at all, I would say it's the egg. So another way of putting this is that galaxies, contrary to many stories that are told, are forming from the inside out. The first thing to happen is this star cluster that does this thing, and then the rest of the giant galaxy forms in the dark matter potential well, etc., etc. Now, the most common explanation of this, what are called, my colleagues, Mitch Spiegelman and Martin Rees, called them a long time ago quasi-stars, which are basically million solar mass black holes with envelopes around them that behave like a sort of radiation-dominated stellar envelope, and they can pulse and so on. And here's a sort of cartoon of one, if you like. As with the discovery of quasars, this is very sensible. There were many things that were on the table at that point. There were nutty things, but there were many things that were on the table at that point. And this is, and this I think is probably a very good candidate for what's actually going on. Two things that worry me about this are the fragility of this radiation-dominated envelope. And the second one is the absence of any double radio sources. We know from gamma ray bursts and so on, put a spinning black hole in the middle of a gas cloud, and the first thing it wants to do is to make a jet. And there's none of that. So that worries me. So the alternative is that the nuclear star cluster that I've just described, a purely hypothetical construct, is what is actually at work here, and and it's a sort of slight variation, if you like. Other people have suggested this too, so it's not, it's not completely original or anything like that, because there's been lots of thinking about this in the past, and it can account for the this can of course account for the rapid growth of luminous quasars, which are being seen out to impressively large redshifts in the early universe. So that this came out there, and we're working. There's a whole lot of physics problems associated with this, and even before comparison with the observation, to see whether this makes any sense at all. So that's where we are, and this is very much work in progress. And here's my summary: low mass supply holes, ETA, semi spin part. The binary black holes may have been found. You can make up your own mind if you believe that. The high mass supply rates may. This is a sort of should be emboldened here, may also be spin powered. That's a conjecture, if you like, and there's little right red dots might be a black hole cluster formed from the first stars. Okay, thank you very much indeed. I've had a great time talking with people here, and I thank you for your hospitality.
Thank you so much for the great talk, Professor Blandford. I have a basic question, and apologies if you already mentioned it. But the particles that emit radiation in the black hole jets.
Sorry, could you say that again? I didn't quite catch it.
The particles that emit radiation in the black hole jets.
Yes?
Where do those particles come from? Are they produced in the jet itself, or are they launched from the accretion disk?
Which jets are we talking about?
The black hole jets.
But which black holes?
The supermassive black holes.
Supermassive black holes. So we get just that. Okay. Again, you'll hear different answers from different people. My own view is that the field lines that cross the horizon close to the black hole are so they're sort of unstable in a small way, and they're shuffling around all the time, just like field lines that are crossing planetary magnetospheres, and they carry plasma from the surrounding gas into the jet. Now, there's a construct called a spark gap, which is relies on this 10 exavolts of potential difference in M87 to make electron-positron pairs to make the jets. I don't think that's necessary. Having said that, I actually think these are sparking all the time. But I don't think it's actually necessary. Just to give you a quantitative estimate for this, the minimum pair pressure to the maximum pair pressure in these systems is the ratio of the Larmor radius to the black hole, which is something like 10 to the minus 12. So you only need a tiny amount of plasma to carry the currents. And so just a little bit crossing those field lines will get you there. So where does the plasma come that's responsible for the gamma rays and the radio and the optical and so on in these jets? It's entrained into the jet. Here's the jet, ultra-relativistic jet. There's a wind like that. There's a wall usually called the sheath. It has other names, but the sheath is the most common name. And you can think about that either as a boundary layer or as a current sheet. It doesn't really matter. But there's entrainment of gas from this wind or whatever is outside it. We would say a wind, but other people would say something different. There's an entrainment all the time. Plenty of gas there. Then you've got 10 exavolts of potential difference. Any fool can make relativistic electrons out of that. Making ultra high energy cosmic rays is a bit more of a challenge, but even that can be done.
So you presented a very nice picture of this division between spin-powered and accretion-powered black holes, both at the high mass case and the X-ray binary case. Can you speak a little bit about the impact on the mass function you would expect from that if you have this transition between, there's a special range of accretion rates at which you can be accretion-powered and grow, and everywhere else you're spin-powered with a decretion disk? Should there be some bifurcation in the mass function, a shallow part?
That's an interesting idea. I think the short answer is no, but that's not because I don't take it seriously. I take it very seriously. And I think it's the sort of thing you might be thinking of. The thing that's going to make it hard to see observationally is because we've got, we see in our galactic center, we've got a rather pathetic black hole of 4 million solar masses. And we've got 20 billion solar masses in other sources. And what constitutes, the ratio of the mass supply rate to the critical mass supply rate varies over 4 or more orders of magnitude. So it's going to be rather hard to see it, but I think...
Well, I guess my comment would be, shouldn't the resultant mass function be a consequence of this division?
Oh,
so there's a reason that you have things at 4 solar masses and 20 that's maybe not just driven by the seed mass.
Oh, I don't think it's got much to do with the seed mass. I think it's got much more to do with the history.
Right.
Yeah, and they're all different. I mean, one of the things I get in trouble for saying, particularly with cosmologists, is that I think galaxies are more different from one another than people. And so, and if you look at them at high redshift, they're even more so. And so it's, they all have these idiosyncratic personal histories. And some of them had lots of mergers and major mergers. Some of them had a few minor mergers and nothing else, and so on. Spirals are different from ellipticals. Things in clusters are different, and so on. It's it's a huge, entertaining variety, and it's very surprising then that the M sigma relations and so on work as well as they do. But it's surprise, but it's surprising that type 1a supernovae work as well as they do. So it's I don't have a good answer for you than that, but absolutely, I completely agree. That's a very important thing to think about.
Yeah, I'm intrigued by ideas about the red dots, but my question is about SS433. You say these bullets are formed in the inner disk and they come out at a quarter light speed.
Yes.
What are these? Are they about the trigger mechanism there, magnetic recombination or something like that?
That's an excellent exercise for the student. I don't know. Let's say I think we'll get. I mean, I have some cartoonish ideas. Basically, you build up toroidal magnetic field, and when you build up toroidal magnetic field, the accretion disk generalization, the Harper instability, can stand stuff up when the magnetic stress becomes too large. And so I would imagine it's something like that.
So it's a cyclic process that you.
Oh, yes, a cyclic process. And I did sort of say, and I was oversimplifying, that they happened about once a day. You may also recall I said 27 hours for a period. Okay, so and it's probably a pretty strongly elliptical orbit. So that I think is what's sort of triggering this.
Okay.
But it's more, I have to believe it's more complicated than what I just said. I'd love to talk about it, but yeah.
Go ahead.
Waiting for my turn. So my question is about the quasi-star, proposal for little red dots, and I think you alluded to this problem already, but it bothers me that where's the angular momentum? Because everything else about black holes is sort of disks and jets, and yet the nominal explanation for these things is suddenly we have this large black hole surrounded by this poofy sphere of gas. And that just doesn't seem like an arrangement that would be easy to maintain. It should be spinning, stuff should fall in and go out.
Yes. I think you've pointed out something that has. I mean, these are my colleagues, and I've talked with them about it. Who do this, and I think that's a concern. But I think all of these explanations have concerns. I don't have a good answer for you. And it's, I would say not making the radio sources is another thing. That the rotation exacerbates the instability. And so I completely agree with you, but I would also admit that there are things that worry one about the story I told as an alternative. It'll be, I kind of think that within a few years, most reasonable people will agree that what is most likely going on in these, and what their role is in the life history of galaxies, that'll be a sort of, I kind of imagine we'll have good answers to that question, but I don't think we have them yet. And it's just like the early days of quasars. People talked about star clusters, they talked about superstars, they talked about black holes. All of these things were on the table. And then there were nutty things like 3C273 being shot out of 3C274, which is M87. But the sensible things were reasonable things to think about. And then we sort of got an answer. And I think the same will happen here. So I look forward to that time.
All right, last one, Dan.
Reggie, a lot to think about that you've given me here. I'm trying to get my hands around one of, well, many things, but one you can quickly speak to. You talked about coherent gravitational radiation.
Yes.
And, I mean, I agree. The result from nanograv Ryan created out of populations of black holes as we understand them, it seems like, boy, it's hard to get a signal that big. And especially when you can't find a black hole binary, after searching for 50 years.
Yes.
So, but in what sense is this radiation coherent? Or is there is there coupling between binaries?
No.
Or is it just you're using a quadrupole from a bunch of mass in bars in this collapsing structure?
Think about the series of papers, and indeed a book that Chandrasekhar wrote in the around about 1970 on ellipsoidal figures of equilibrium. In fact, I have a student who is of Indian descent, and I tell him that the problem he's working, it's an undergraduate, the problem he's working on is the one that Chandrasekhar did not even start on. But he's unfazed. Basically, think about this as a fluid model. And that's what he's doing. He's making a fluid model, putting in the Newtonian dynamics, essentially, and then the gravitational radiation reaction. And in principle, you can make gravitational radiation reaction grow in instability or not. And the rough rule for when this happens is not, it fails, but typically a good sign is if the backwardly directed instability is going forward in the inertial frame. Now, I don't know, I'm eager to talk to Sam about all of this stuff who have a more sophisticated view than I do, but I think we're trying to understand if you can actually drive an instability when you get sort of 15% of the gravitational energy and rotational energy in one of these systems. And I don't know if that even works. That's one of the ways this can fail, is if we can't make coherent gravitational radiation. But that's a work in progress.
Yeah, I know there's more questions. I think we better let people go. Roger will be viewable at low redshift today. So please do come find him after the talk, or one of those days to ask him more questions.